Okay, so now we're moving into the decay models. And just like the growth models, we're going to be using the exact same generic formula. And that generic formula, in case you had forgotten, looks like P equals P sub 0 times e to the kt. T is time, P sub 0 is the initial amount, the ending P, or the P over here on the left is the ending amount, and the K is the rate. Now in the growth models, the rate was positive. Since in this particular lecture we're talking about decay models, your rate will be negative. So let's look at the first problem that we actually have been given. It reads, the amount of carbon-14 present in animal bones T years after the animal's death is given by this function. They want to know how old the ivory tusk is that has lost 28% of its carbon-14 content. Okay, so a little side note, archaeologists actually measure carbon-14 to determine how old an animal was when it passed away, okay, or how long ago it passed away, all right? So just a little side note, this actually is a real life problem, and they've already come up with the formula for us to use. So here's the deal. They did tell us T was in years, correct? So let's mark that down. So T, that's in years. They also said how old, right? The question was how old, so they're looking for T. So if they're looking for the time, then we need to know the initial amount, don't we? But not only do we need to know the initial amount, we also need to know the ending balance. Because if T is the only variable that I'm supposed to be solving for, that means P sub 0 and the P of T need to be known. Well, remember what they said. They said that the ivory tusk lost 28% of the carbon-14. So here's my question. If it lost 28%, then how much still remains? Good. 72% still remains, doesn't it? And some of you are like, how'd you get that? Well, help me out. What's the most percentage you can ever get? And I'm not talking about extra credit. I'm not talking about the retail industries, which hikes their prices up well over, right, the top percentage. What's the most percentage we can have? Yeah, 100%. So if the most we can have is 100% and 28% was lost, then how much remains? Good, 72%. By the way, that leads me to my next question. What's the actual initial amount then? Now, they never gave us a weight. They never said this many grams or this many pounds or anything else, did they? But they did tell us, or we figured out, that 72% remained. So if 72% remains, how much did they start with? Good, 100%. So here's the deal. Now that we've got that figured out, here's the deal. We now know that P sub 0 stands for the initial amount, and so P sub 0 is 100%, but remember, we never use it with a percent sign, so how do you write 100% as a decimal? Yeah, 1.00, right, or just 1. And the ending amount, P at whatever time that is how much? Yep, 72% remains, but again, we don't use it with a percent sign. Good, we use it as a decimal, so 0.72, correct? All right, looks like I can start setting up my equation. So, the ending amount, which we said was 72, equals the initial amount, which is 1, multiplied by e to the, yeah, they gave us the k, didn't they? All right, multiplied by t. Okay, got to solve for t, so what do we do? Yeah, well, 1 times this is just the e to the whatever, right? So on the next line, some of you should just write this. Why? Because you're visual and you need to just get that 1 out of your sight. All right, so I need to get to the T. What do I get rid of now? Good, get rid of the E. So what do we do? Natural log on both sides. Excellent. So natural log it on both sides gives me this over here on the right. Then what? Good, divide by that negative wonderful little decimal. I know, some of you got your calculators out already. As a matter of fact, you're starting a calculator punch as I'm writing this next line. But my recommendation to you is write the next line so you finger punch correctly. Now, after you're done finger punching, they ask you to round to the nearest integer. And yeah, I'm assuming you know what an integer is and that you know how to round correctly, right? By the way, this is still an approximation because you are rounding. Now, I don't know about you, but I ended up with 2,716. Did we agree? I hope we did, because if we didn't, either I finger punched wrong or you finger punched wrong. But, you know, we're all human, so every once in a while that stuff happens, right? So that means that this, what are they talking about? These animal bones are 2,716 years old. Good? Excellent. Hang in there. Got another one. All right, so let's look at the next problem. It says, of an initial amount of 6,000 grams of lead to 10, how much remains in 170 years? Oh, and by the way, lead to 10 decays at a rate of 3.15% per year. Okay, so they didn't give us any formula for this one, so you're like, well, how do I know what kind of model it is? Well, if you notice, it gave you a decay rate. So as soon as it gives you a decay rate, the implication is that you are dealing with an exponential decay model, which means our formula looks like this. Correct? Okay. So, whoops, I forgot something. Some of you noticed. Yeah. So here's the deal. What did they give us? They gave us an initial amount, which is the P sub 0, isn't it? Okay, so let me just rewrite the formula over here. So they gave us an initial amount, which is 6,000 grams. E, right? E is not a variable. E represents a number. They actually gave me a decay rate. Now, how do you write 3.15% as a decimal? Good, 0.035. But since it's decay, it's got to be a negative 0.035. Agreed? Okay. And then the time is 170 years, isn't it? All right. And over here, I'm looking for the ending balance at time 170 years. Because technically this is a function, so you would write it as P of t. The population or the ending amount at time t. If you remember from the last, the exponential growth lecture video, the P could be written as any kind of variable. Sometimes they use N, sometimes they use P, whatever floats their boat, okay? All right, so easily done. They actually gave us everything what we need. All we need to do is calculator punch, right? Okay, so pause the video and come back when you got your answer. And by the way, it says round to 1 decimal place. Go ahead, I'll wait. You got it? Okay, so hopefully we agree. I got 28.3 grams are going to remain after 170 years. Well, that's not a lot, is it? Right? That's 170 years, isn't it? Okay, so hopefully you and I got the same answer. Did we? Cool. Stay tuned. Got another one. Okay, so let's look at the next problem. The decay rate for a particular radioactive element is 2.1%, where time is measured in years. Find the half-life of the element. Okay, so they gave us a decay rate, didn't they? Which means we've got what kind of model? Good. An exponential decay model. So the formula looks like, and let's be more specific, the P of t, like population at time t, or in this case it didn't really tell us it was a population, but P sub 0 e to the kt, correct? Okay, now, they gave us a decay rate of 2.1%. So how do you write 2.1%? Good, 0.021. Agreed. But since it's a decay rate, yeah, you're going to put a negative in front of it, aren't you? Now here's the interesting thing. They're talking about half-life. They want to know the half-life of the element. Well, let me explain to you what half-life actually means. Half-life means how long does it take for a certain element to decay 50%. For instance, that carbon-14 content that we spoke about a little bit ago, you know, when they look at the bones, they're trying to find the half-life of that carbon-14. And once they know the half-life of that carbon-14, then they know that at that particular point in time, 50% of the carbon-14 has decayed. For example, if I know the half-life of carbon-14 is 5,280 years, then I know when I look at that bone and I measure the carbon-14 content present, I know that after 5,280 years, 50%, half of it, has decayed. All right? So in this particular case, they're talking about some element. All I know is the rate of decay, and I'm trying to find out how long does it take for 50% of that element to decay. Got it? I'm trying to find out how long is it going to take for 50% of that element, for half of that amount in that element to decay. So, here's the interesting thing. They gave me the decay rate. I know it's negative 0.021. They're asking for half-life, which means they're looking for time, which means if they're looking for time, I better know the initial amount. What do you think the initial amount is going to be? And maybe here's another question that'll help you out. What is going to be the ending amount? Remember, half-life means how much of the element has decayed. Okay, good. So then how much of the element actually remains? That's right. 50% of it actually remains. So then how much was initially present? 100%. Good. Does that make sense? Okay. So that being the case, that means my ending amount is 0.5. My initial amount is 1. E to the, good, negative 0.021 multiplied by t, because I'm trying to find t. Agreed? Okay, so on the right side, yeah, multiply that 1. And so this is what the right side looks like. It's a little cleaned up. Now what? Good, natural log on both sides, because that's how you're going to get rid of that e, correct? And then what? Divide by that negative 0.021. And I know you got your calcs out already, which is fine. It's good to have them handy for these problems because you're going to need them for these problems. And the directions say to round to 1 decimal place. So, what did you get? Yeah, you know, when you round to the 1 decimal place, it actually bumps it over. So I've got the half-life is actually 33 years. So, that means that this particular element, radioactive element, that has a decay rate of 2.1%, in 33 years, half of that radioactive element has decayed. Cool? By the way, it doesn't mean it'll take another 33 years for the rest of it to decay. It actually could take longer for the last 50% to decay. You're like, why? That's not my field of expertise. Go ask somebody who's in that field. But anyway, Got the picture? Cool. Be right back with another problem. Here's the next one. The half-life, capital T, for a particular radioactive element is 11 minutes. Now they want you to find the decay rate. Well, what kind of model is it? Good, a decay model, which means, excellent, write the formula down, right? The generic formula, P of T equals P sub 0. What does that represent? Initial amount, excellent, times e to the k. What's k? Good, the rate, times t, which is time. Good. Okay, the last problem, we spoke about a half-life, didn't we? Half-life means what? Yes, 50% is decayed, which means how much is left? Good, 50%. So then what's the initial amount? Excellent, 100%. Good job, you guys. Okay, so that means, yeah, now you've got an idea of how to write the formula. So you know that 50% remains, 100% is the initial, e to the, yeah, they're looking for the rate, aren't they? So we leave it alone. It's a decay rate, I know. Just leave it as k times multiplied by the time, which is, which is 11. That t should be a k, by the way. Sorry about that. And I know some of you are going, well, shouldn't that k be negative? Don't worry about that. It will work itself out in the end. Trust me. Okay? I know the authors of your book may put it as a negative, and that's fine. But there's a reason I don't. Okay? It'll work out. Trust me. Okay, so let's solve. Okay? We know how to solve this. How do I get rid of that e? Good. Natural log on both sides. And then what? Good. Divide both sides by 11. Okay, I know you've got those calcs out. What did you guys get? And they say, by the way, round to the nearest tenth. By the way, do you notice it says don't round to the final answer? This is why I don't have my calculator out until I've got the variable by itself. Okay, so when you round to the nearest tenth, hopefully you got the same thing I did, which is a negative 6.3. Is that what you got? Good. So here's the deal. The negative tells me it's a decay, which is why I don't put the negative in the beginning, because I want to make certain that my rate is negative, which means I'm really dealing with a decay model. So I'm going to tell them that the decay rate is 6.3%. Why don't I put the negative? Because I put the word decay. The decay rate is 6.3%, which automatically means the rate is negative. Good? Hang in there. Got it. Okay, let's look at the next one. Uranium 238, and they give you an acronym for it, U-238, has a half-life of 4.5 billion years. Geologists find that a rock containing a mixture of U-238 and lead, and determine that 78% of the original U-238 remains. The other 22% has decayed into lead. And they want to know how old the rock is. Okay, so some of you may be going, well, what is this model? And some of you are assuming it's an exponential decay model, and I get it because that's what this whole lecture video is on. But you got to understand what the key words are here so you know, you understand why it's a decay model. The word half-life means it's decaying. So it's a decay model because it said half-life. Got it? Okay, so, yep, our handy-dandy formula. You guys are getting the hang of it, right? Okay, now, half-life is 4.5 billion years, isn't it? Good. I'm not going to write the billion, by the way. That's a lot of zeros. That's just going to get in the way of our computations. But my unit, so to speak, is in billion. All right? Now, here's the key. I know they said that this rock contains U-238 and lead. I understand that it has both of them in there. But they gave me half-life based upon which element? Based upon 238. This whole formula is going to be on the element U-238. I don't care about the lead. I don't care what happens to the lead in the rock. All I care about is the U-238 element because they gave me the half-life of that U-238 element. Got it? Okay, so here we go. We have 78% of that U-238 remaining. What's the 78% represent? Good, if that's the remain, that's your ending, isn't it? So we've got 0.78. So then how much U-238 did we have to start? 100%. Excellent. E to the, yeah, they're asking, oh, interesting, right? Wait, let me back up. They didn't give, wait, hold on. They didn't give me the K, did they? All they told me was that the half-life is 4.5, but I don't have the K, do I? Well, how the heck am I supposed to figure out how old this rock is if I don't know the rate? All right, hold on to this a second, okay? I'm going to get rid of this KT for a second. Why? Because I can't do anything with that information yet, can I? All right, here's the thing. They didn't give us the rate, did they? First, find the rate. That's going to be key. I need to find the K. And the way we're going to do it, we know the original amount 100%. E to the 4.5 K, because I'm looking for the rate, agreed? And now 4.5 is the half-life, isn't it? Well, if that's the half-life, and I know 100% is started, then what remains? Good, 50%. Excellent. Does that make sense? Okay, so when I work this out, I am going to do what I have been doing, right? I've got to take the natural log of both sides, and then finally, to find the K, I'm going to take the natural log of 0.5 and divide by 4.5, right? Okay, so what did you guys get for K? And I'm going to round to 3 decimal places. Negative 0.154. And some of you are like, how do you know how much to round? In actuality, I'm going to leave that number in my calculator. Why? Because I don't want to round this. I want to round at the final answer. So in actuality, now that I've got the K rate, which is this really, thankfully it's negative because it was supposed to be decay, I know how to finish setting this up. Because in actuality, this was asking me how old is the rock. So we're looking for what? Yeah, we're looking for time over here. So that means I am going to substitute in this lovely natural log of 0.5 divided by 4.5, and I'm going to multiply it by T, because I'm looking for time. So let me pause a second. I tried to set this formula up, but I couldn't go very far because I didn't have the rate. Gratefully, since I had a half-life, I knew the ending amount was 50% and the initial amount was 100%. Solve like I normally do. Gratefully, my rate turned out to be a negative number, which I needed it to be since it was a decay. Agreed? And I am actually going to use this as my rate because I don't really want to round the decimal. I don't want to round till the very end. I want this as accurate as possible. Got it? Okay, so now when I go looking for how old this rock is, that started at how old the rock is, that had 100% U-238 and 78% of the U-238 remained, Now I can set it up because there's my decay rate. Does that make sense? Good. Okay, so I am just multiplying by the 1. All right, how do I get rid of that e? Natural log it, just like we did over here, right? So I'm going to take the natural log of this. And yeah, I end up still with this natural log over here, right? Multiplied by t, and to get the t by itself, good, you got to divide both sides by this lovely fraction, which is the natural log of 0.5 over 4.5. And now the calculator punching comes in, and it says to round to 3 decimal places at the very end. So when I do that, I get t is 1.613. Did you get the same? Okay, but it's not 1.613 years, it's 1.63 billion years. And this is where your billions comes back in. Cool? All right, stay tuned. Got another one. So let's look at the next problem. A chemical substance has a decay rate of 8% per day. The rate of change of an amount, capital N, of the chemical after T days is given by this particular formula. So notice what they said, the rate of change. Rate of change means the derivative. So the derivative of N with respect to T is given by this formula, correct? They also told us the decay rate per day is 8%. Good? Okay, so now that we understand what they've given us, let's get to part A. Part A is saying, let N sub 0 represent the initial amount of a substance present at T equals 0. Find the exponential function that models the decay. So in the beginning they said decay rate. In part A, they're saying models the decay. So clearly I am working with a decay model. Agreed? An exponential decay model. So notice in this particular case they're using N as the variable. So N of T, right, our ending amount is equal to the initial amount times e to the kt. Agreed? Okay. Now in part A they were very specific. N sub 0 represents the initial amount at time t. They didn't give me an actual number. They just said let it be N sub 0. Fine. But they did say that we had a decay rate of 8% per day. So that means that my model is looking like negative 0.08 t. Good? I can't fill in the initial amount because they said the initial amount is N sub 0. So that's really as far as I can take part A. There's the model I'm working with. Make sense? Okay. Then let's look at part B. Suppose that 300 grams of the substance is present at T equals 0. Okay, so hang in there for a second before we read any more. Suppose that 300 grams of the substance is present at T equals 0. What does that 300 grams represent? Yeah, the 300 grams actually represents the initial amount, doesn't it? So the initial amount now, according to part B, is 300 grams. Then it wants to know how much will remain after 2 days. So 2 days represents what? Time. Okay, so I know that the time in days is 2. So use the formula from part A, right? So the ending amount at 2 days is equal to the initial amount, which is 300, multiplied by e to the negative 0.08 times 2. Okay, I know you got your calculators out. Be my guest. Finger punch. I'm waiting. What'd you get? Okay, I think we got the same thing. What did I get? And by the way, round to 1 decimal place, please. So, the ending amount after 2 days is approximately 255.6 grams. At least that's what I got. Hopefully we agree. And if we didn't, that means one of us finger punched incorrectly. But we both agree on the formula, so that's what counts too. Good? Okay, let's look at part C. What is the rate of change of the amount of the substance after 2 days? All right, so what's rate of change mean? Yep, the derivative. Okay, so we have part C, right? We have the rate of change. This was the formula they gave me, wasn't it? Okay, but hang in there 1 second. So using the formula we got from part A, and I'm just writing this down, to find the derivative, when I take the derivative of an exponential function, it's the exponential function itself multiplied by the derivative of the power. Correct? Okay. And if I want the rate of change after 2 days, that means I am looking for the rate of change at time is 2. Correct? So if I plug this in, isn't this first parenthesis, isn't this parenthesis right here just the exact same thing there? The part B, isn't that this amount right here? It is, isn't it? So really, the rate of change after 2 days is equal to the original function after 2 days multiplied by the negative 0.08. And when I take my 255.6 grams and multiply by the negative 0.08, what did you guys get? By the way, round to 1 decimal place, please. Let's see. Did we get the same thing? I got negative 20.5 grams per day. So we have a decay, and it is a decay model. So they're losing about little over 20 grams per day after 2 days. Cool? Okay. And there's a part D. Part D is saying, after how many days will half of the original amount of 300 grams of the substance remain? Okay, this sounds familiar, doesn't it? Yeah, it's like a half-life, isn't it? Because they want to know how many days is it going to take for half of this thing to decay. So if we start with 300 grams, yeah, then we end at 150 grams. But I got a question. Do I use this original function here, right, except we don't know the 2, or do I use the derivative? Yeah, I'm using the original function. Very good. Why? Because it didn't say rate of change in part D. Part D didn't say anything about a rate of change. It just wants the half-life. So we end with 150 grams. We started with 300 e to the negative 0.08 t, right? Okay, now what? Good, divide by 300, which will give me 0.5 when I actually do that, right? I get half. E to the negative 0.08 t. Now what? Natural log of both sides to get rid of the e. Very good. Of 0.5. Now what? Divide by that negative 0.0. See, a lot of this, I mean, to solve this, you got to know to take the natural log, but then after this, it's all algebra. So you need to make sure that you're good with your algebra skills, right? Okay, round to 1 decimal place because I know you're finger punching. So what'd you get? You got 8.7. All right. What's my units? 8.7 what? Days. Because it's the decay rate per day. So this is going to take 8.7 days for half of this 300 grams of whatever substance it is. It's going to take 8.7 days for half of that substance to decay, according to this model. Good? Stay tuned. Got another one.